Clear
Yes, sir.
and audible? Okay.
Yes, sir.
Yeah. Do you have any doubts till now? Do you have any doubts? No. Right. So signal can be classified based on the number of independent variables. Okay, so at the bottom you can see one-dimensional signals, speech, music, computer data, all these comes under one dimension. Two-dimensional signals means pictures or digital images. Three-dimensional signals means video. Four-dimensional signals means volume over time. Okay, like this you can have multi-dimensional signals or one-dimensional signals. The next category is a continuous or a discrete. Now the other point is we have seen the number of independent variables, either it can be one or multi. Now we are discussing that how about the independent variable, whether it is continuous in nature or discrete in nature. Suppose if it is continuous, then the signal is said to be continuous time signal. So you can see the independent variable here is time, and it is continuous in nature. It is defined for each and every possible of t here. Okay, only it's not like only finite number of instants the signal is defined. Okay, the second case is suppose a signal whose independent variable is discrete in nature. That means a finite number of instants are there. Finite number of instants. So -3 to +3 means overall 7 instants are there. -3, -2, -1, 0, 1, 2, 3. 3 plus 3 and including 0 becomes 7. Only 7 finite number of instants. And these instants are being defined at -3, -2, -1, possibly integer values. Okay, then such signal is said to be discrete in nature. Okay, or more precisely discrete time signal. More precisely discrete time signal. Okay, now so till now we have seen independent variable, either it is one or multi. After that we have seen whether this independent variable is continuous or discrete. Now we'll come to the y-axis or the amplitude or magnitude. Okay, where we try to represent the quantity of the signal. The quantity of the signal, you can see here the quantity of the signal. Okay, so if you look at the quantity of the signal on y-axis, it is continuous. Okay, it is continuous, right? It is not having finite values, it is having infinite values. Okay, so a signal whose amplitude can take on any value in a continuous range, any value in a continuous range, then that signal is said to be analog signal. Then that signal is said to be analog signal. On the contrary, digital signal, it will have finite values, finite number of values. So now you can see this is one value, another value, like this you can count finite number of values are there. And in some cases it can be 2 or 3 or 4 also. If it is 2, then we'll call it as a binary signal. Okay, so now you can see here as the amplitude, 1 minute, 1 minute. Yeah, if it is finite in number, okay, and 2 in number, then it is called as binary. Only 2 are there, or otherwise it is said to be digital signal. Otherwise it is said to be digital signal. Okay, binary signal or digital signal. So what is the difference between binary and digital signal? So your discrete version of the signal, if the discrete levels are 2 in number, then it is said to be binary. So on the broadest context, we will call this as digital signal. It can be finite values. If you say purely binary, means only 2 levels are there. For a digital signal, finite number of levels are there. That point you have to remember. Now we'll go back. Here it is a continuous time analog. This is discrete time analog. Discrete time analog means this is analog signal. Okay. Continuous values of amplitudes are being defined, but the time is discretized in nature. It is defined only at this instant, defined at this instant, defined at this instant. So the time is discretized. Okay, that is the basic difference. Similarly, for digital also you can have continuous time digital. It is defined over the continuous range of time. Whereas here this particular signal discrete time digital. Discrete time digital means the time is discrete. What about the amplitude? Amplitude is digital. That means finite. Amplitude is finite. Okay, that is the difference. Okay, now do you got the difference between analog, digital, or continuous and discrete? Any doubts? Any doubts? No. Right, we'll move ahead. The next one is you are aware of the functions, and a function x is said to be even if it satisfies this condition x of t equal to x of minus t for all t. X of t equal to x of minus t for all t values. And in a similar way, you can define it for sequence, discrete version. You don't bother about this t and t, n. This t in general, the standard is this is used for continuous time signals. N is used for discretized signals, or we will call this discrete time signal also as a sequence. Okay, right? It is a sequence. Okay, right? A sequence x is said to be even if it satisfies x of n equal to x of minus n. That means even if you reverse the signal, okay, from both the ways, it seems to be the actual signal. For example, you can see, we can say simply it is symmetric about the origin. Okay, that means if you take a positive value of t equal to 1, there is some amplitude like this. Okay, the amplitude will be same at t equal to minus 1, the same amplitude. Okay, at 2 it is 0, at minus 2 it should be 0, then only this particular equation holds good, x of t equal to x of minus. So if it is possible for all t, if it is possible for all possible t, okay, the value of x of t is equal to value of x of minus t, then such signal is said to be even. Okay, similarly you can verify it for x of n equal to 1, then it should be equal to n equal to minus 1. N equal to 2, it is having some amplitude 2, then what is the amplitude at n equal to minus 2? 2 once again. N equal to 3, the amplitude is 1. Then what is the amplitude at n equal to minus 3? It is also 1. So like this, if x of n is equal to x of minus n for all possible n values, and it is behaving symmetrically about the origin, you can fold it about the y-axis. You can fold it by this line. Okay. So these amplitudes will match. Okay. If you fold this like this about the y-axis, then it is symmetric. Okay, but on the contrary, you have the odd signal. What is odd signal? X of t is equal to minus x of minus t. X of t is equal to minus x of minus t. Similarly, for sequence, x of n equal to minus x of minus t. So now you can see, first we will discuss about the discrete sequence. So at 0, okay, at minus 1, see here, n equal to 1, the amplitude is 1. Then what about the n equal to minus 1? It should be minus 1. Okay, n equal to 2, the amplitude is 2. Then what is the value at n equal to minus 2? It is minus 2. Okay, like this, if x of n is equal to minus x of minus n for all n, then that signal is said to be odd. Similarly, for x of t, you can see here, this direction is like this, positive quantities from 0 to 2. From 0 to minus 2, the quantities are negative, and so on. Reverse is the case here. Negative values, okay, from 2 to 3. Then from minus 2 to 3, positive values. So now you can see that this equation is satisfied. X of t is equal to minus x of minus t for all t. Okay, for all t, right? So these how you can define even and odd signals. So this type of signal is said to be odd signal. Why we require these things? We will be using these features while analyzing these signals in a better manner. Okay, right? Do you have any doubts? Do you have any doubts, students?
No, sir.
Can anybody summarize what we have discussed in this class? Quickly summarize. Lateral entry 1, LE1, Srikanth.
Sir.
Yeah, can you
Yes, sir.
summarize what we have learned, what we have discussed? Quickly, what at least you have remembered.
Classification of signals
Okay.
and example
Hmm.
and continuous and discrete signals.
Hmm.
Analog signals, digital signals.
Okay. What do you mean by
Next,
continuous time signal?
Continuous
See, Srikanth,
signal with
if
sir,
that much
continuous
disturbance is there,
independent.
see, Srikanth, if that much
Yes, sir.
disturbance is there while class is going on, then how you can concentrate? It will be a problem. Is it not?
Yes, sir.
You have to sit in a place where there is no disturbance. The room noise is not there. Hmm. Okay.
Okay, sir.
Hmm.
Okay.
Right. Good. Good. At least you have made an attempt. So initially we discussed about the significance of signals and systems and how these things are very essential for us in learning and in developing in designing the systems for signal processing activities and in further courses also, right? And later on we discussed about a signal definition followed by signal examples, and later on we discussed this classification of signals, and we have seen around 2 to 3 categories like continuous and discrete type signals, analog and digital signals, and third one even and odd signals. Maybe we'll continue with this one in the next class also. Another 2 to 3 versions are there, category of signals, we'll complete it. Okay.